Hi everyone! Today let's talk about session 14.2, Finite-difference methods for linear ODEs. So for the higher order ODEs considered in the previous sessions, all the required information about the solutions is specified at the same point x0, right? Which is called the initial conditions. But in many important applications, the information that is known about the desired solution is given at the endpoint of an interval AB. Such problems are called ordinary differential equations boundary value problem, BVP. So IVP is initial value problem, BVP is boundary value problems. Okay, the finite difference method is based on dividing the interval of interest into a number of subintervals and replace the derivatives by appropriate finite difference approximations. So here, given a general linear two-point boundary value problem. Okay, so it's second order. Do you still remember what linear ODE means? It means that we have a linear combination of the y and the derivatives. Okay, and the coefficient functions, they are functions of x. So you won't see like a y squared or sine y or e to the xy in the differential equation. No, not those. Okay, so this is a linear ODE. Okay, suppose we have a second order linear ODE. Okay, with the boundary conditions. So y of a equals alpha, y of b equals beta. So we have a point A and B here. Then we divide the interval AB into n subintervals. So this is x. A is like x0, and then we have x1, x2, x3, dot dot dot. B is like xn. And then the step size h equals b minus a over n. Okay, then to approximate the functions at the point x1, usually because we know y0 equals alpha and we know yn equals beta, right? So we're looking for y1, y2, and yn minus 1. So those are the unknown. All right, we can in order to approximate those points, we can use the central difference formula. Okay, so see, these are the central difference formula. This is for the second derivative, this is for the first derivative. We studied that in session 11.1. Do you still remember that? Central difference formula. And then we can substitute these expressions into the boundary value problem. So substitute into these differential equations. We get this is equations with the unknown yi plus 1, yi, and yi minus 1. Okay, so here for I equals 1 to n minus 1, we get a system of n minus equations of n minus 1 unknowns. So here we have n minus 2 unknowns. Okay, we need n minus 2 equations. But we just look at the I goes from 1 to n minus 1, we can get those n minus 2 equations. So n minus 1 unknown, and we have n minus 2 unknown, and n minus 2 equations can help us to solve the unknown. Okay? Alright, so let's look at the first example. Approximate the solution of the boundary value problem using finite difference method with n equals 4 subinterval. So first, we draw the picture. Here we divide it into 4 subinterval. Okay, so see y of 0 is 10, so this is 0, this is 4, the midpoint is 2, then this is 1, this is 3. So this is like the A or x0, x1, x2, x3, x4. And the corresponding, we have y0, y1, y2, y3, y4. And we know that y of 0, so y0 is 10, y of 4, this is y4 is 2. So far so good, and we are looking for y1, y2, and y3. So here we have 3 unknowns. So far so good, And what is h? Well, h is the step size. In this case, it's 1. And we know this b minus a over n, right? So b is 4 minus 0 over n, which is 4. So this is 1. Okay, so okay, next we need to plug in the central difference formula. So here, these are the central difference formula. Okay, so y prime prime equal approximately by yi plus 1 minus 2yi plus yi minus 1 over h squared. And then the y prime is approximately by yi plus 1 minus yi minus 1 over 2h. So plug this in the differential equation. So first we have y double prime. So yi plus 1 minus 2yi plus yi minus 1 over h squared plus 2 times y prime. Y prime is yi plus 1 minus yi minus 1 over 2h plus y. So yi equals xi squared. So far, so good. So this is what happened when we plug in. Okay. And let's continue. So here, because h equals 1, alright, so let's simplify it. Well, then we get yi plus 1 minus 2yi plus yi minus 1. Here, oh, h is 1, but the 2 and 2 can cancel. So we just have yi plus 1 minus yi minus 1 plus yi equals xi squared. So we want to simplify so that the left-hand side we have yi minus 1 and yi plus 1. And on the right-hand side, we have the constant terms or functions of x. Okay, so here, let's see. So let's see, how many yi minus 1 are there? You see, yi minus 1, they actually cancel out. How many yi are there? We have minus 2yi, and here we have 1 yi, so we have negative yi. How many yi plus 1 there? 2 copies of yi plus 1, and that equals xi squared. So far, so good, everybody? So this is the formula we get. Now, let me make this smaller so that I can have more space. Alright, we're ready. So here we plug in I equals 1. See, we're looking for y1, y2, y3. So we plug in I equals 1, I equals 2, and I equals 3 so that we can get 3 equations to solve those 3 unknowns. Okay, when we plug in I equals 1, we get minus y1 plus 2y2 equals x1 squared. And what is that? Well, y1 is what we want, right? So we have minus y1 plus 2y2 equals x1 is 1. 1 squared is 1. Okay, so and when I equals to 2, we plug in minus y2 plus 2y3 equals x2 squared. So we get minus y2 plus 2y3. x2 is 2. 2 squared is 4. When I equals 3, we have minus y3 plus 2y4 equals x4 squared. Okay, so we get, but here, x4 is 4. y4, we know it is actually 2. So we get minus y3 plus 2 times 2 is 4 equals 4 squared. So minus y3 equals 4 squared, which is 16 minus 4 equals 12. Oh, sorry. I make a mistake. this should be x3. x3 is 3. So this is 3 squared. Sorry. Yep. And next we have what? So that is 9 minus 4, which is 5. So y3 equals 5. So far, so good, everybody? Okay, so we get y3 equals 5. Then we can go back and find y2, right? We can go back here and we can plug in. So minus y2 plus 2 times 5 is 10. So minus y2 is 4 minus 10 is minus 6. So y2 equals 6. Let's see. Oh, we realize. So minus y3 equals 5, so y3 is actually minus 5. Then this is minus. Then it will be 4 plus 10 is 14. y2 is then negative 14. Yeah, sometimes we have to be careful because when we work with a lot of numbers, yeah, it's very easy to make mistakes. So we gotta be careful. And then we can plug in the first one. We get minus y1. 2y2 will be minus 28 equals 1. So minus y1 is 1 plus 28 is 29. So y1 is 29. So we get y1 is 29. y2 is minus 14. y3 is negative 5. So far, so good, everybody? Okay, so actually, you can also use matrix to solve y1, y2, y3. How? Look at the first equations. Okay, you can get an augmented coefficient matrix, right? So the augmented coefficient matrix, you want to have a times y equals the right hand side, right? Let's look at the coefficient of y1 is minus 1. Coefficient of y2 is 2. Coefficient of y3 is 0. Right hand side is 1. Second equation. Coefficient of y1 is 0. Coefficient of y2 is minus 1. Coefficient of y3 is 2. Right hand side is 4. Last equation. After we simplify it, y3 equals minus 5. So 0, 0, 1 equals minus 5. And then you can use your calculator to do reduced echelon form. Okay? REF. Then you will get the answer for the matrix. Okay? So then you will get reduced echelon form will give you and the resulting numbers here, those are gonna be our answers. So far, so good, everybody. I can also show you here. So we can use any like matrix. So matrix calculator. You can use your calculator, or I can use this MATLAB or Octave, right? So first row minus 1, 2, 0, 1. Second row 0, minus 1, 2, 4. Last row 0, 0, 1, negative 5. And brackets. Okay, this is the matrix. If we do reduce row echelon form of A, see? We get y1 is minus 29, y2 is minus 14, y3 is minus 5. And that match with our answers. So far, so good, everybody? So this is the finite difference formula. We can also use MATLAB. So these are the syntax for the MATLAB codes. Here, A is the left endpoint of the interval. Okay, so AA is the left endpoint. BB is the right endpoint. n is the number of subintervals, h is b minus a over n, okay? And then x is the linear space, and you use this AAA plus equals AA plus h, comma BB, comma n. Okay, this is like how it increased by the step size. And then the syntax for finite difference method, well, this is the left endpoint, this is the right endpoint, and then this is the n, and then we have the P, Q, R, and then this is the YA, and this is the YB. Okay, what is PQR in this case? Well, PQR is, so if you solve for Y double prime, okay, this guy, if you solve for Y double prime, you get minus 2Y prime plus minus y and then plus x squared, right? So P is minus 2, Q is minus 1, R is x squared, okay? But the P, Q, R are actually vector value functions, okay? So P, Q, R here, they are column vectors, okay? They are so they are column vectors. So the dimension is m minus 1 by 1 column vector. Okay, so if you want to put the vector here, we need to use -2 times 1's and dimension 1, 3. This means, okay, sorry, I don't have enough space here. So let me put it here. -2 times 1's 1, 3. This means it's -2 times the vector 1, 1, 1. Okay, 1's 1, 3. 1, 3 is the dimension, so it means we have a column vector, and then we have the 1, 1, 1 other entries. So Q is -1 times the column vector 1, 1, 1, and R is x squared. But here, very, very important, you have to put the dots there because x is a vector. Okay, x is a vector. So if we put the dot there, it means it's pointwise multiplication and pointwise powers. So each entry in the x vector raised to the power of 2. Okay, but if you don't put the dots, it becomes vector multiplications or matrix multiplication, then the dimension won't match. Right? Remember matrix multiplication? Well, if we have m by n times n by r, then the result is m by r. But a vector x is a n minus 1 by 1 column vector. When you multiply by itself, the dimension won't match. So don't forget this point, the period there. Okay, let me use. Okay, so don't miss this point. Okay, is point wise multiplication or power for vectors. Okay, and 10 is y0, 2 is y4. Okay, after you input those in MATLAB, you get these answers. You see, it match our result. Okay, and we can also plot it. This is the graph. So far, so good, everybody. Okay, I can also show you in Octave. Let me see. Can I just copy it here? Okay. Actually, I just type it. So have these and then have this one. You can see we get the points and we get the graph. So far, so good. Okay, let's continue to look at example 2. approximate the solution of the boundary value problems using finite difference methods. So keep in mind, if we have initial value problem, we learned Euler's method and the Runge-Kruta method. Okay, but for boundary value problem, we can just use this finite difference method. Okay, so now let's see. Here, we have the interval from 2 to 4. 2 to 4. Here, midpoint 3, and we cut it into 4 subintervals. So this is 2.5, this is 3.5. x0, x1, x2, x3, x4, y0, y1, y2, y3, y4. And y0 is -1, y4 is 10. And then here we have 3 equations, 3 unknowns. Okay. And don't forget y prime prime is the central difference formula. By the way, it will be given in the exam, so you don't need to memorize it. So this is yi plus 1 minus 2yi plus yi minus 1 over h squared. And then the y prime is approximately by yi plus 1 minus yi minus 1 over 2h. Well, in this case, h equals 0.5. Okay, now let's plug in. So xi, y prime is yi plus 1 minus 2yi plus yi minus 1. H square, well, that is 0.5 squared, which is 0.25. Plus y prime, which is yi plus 1 minus yi minus 1 over 2 times 0.5 is 1. Plus xi. Okay, so far so good, everybody? Alright. Next, let's continue. So here, do you know what is 1 over 0.25? That is actually 4. Yeah? 1 over 0.25 is actually 4. So we can distribute it. We get 4xi, yi plus 1 minus, 4 times 2 is 8xi, yi plus 4xi, yi minus 1. Plus yi plus 1 minus yi minus 1 plus xi equal to 0. So we want to reorder it. So is the terms of yi minus 1, in this case is 4xi minus 1. And then we want to look at the yi. So minus 8xi yi. And then we look at the yi plus 1. Okay? This is 4xi plus 1. Okay? And then the xi, let's move to the right hand side. So you want to change it in this format. Then it's easier for you to construct a matrix later on. Okay. So after we simplify it, now we start to plug in. Because I equals 1. Then we have 4x1. Okay? 4x1, x1 is 2.5 minus 1. And this is y I minus 1. y1 minus 1 is y0. Minus 8. x1 is 2.5. And then we have y1 plus 4 times 2.5 plus 1. y2 equals minus x1 is 2.5. Okay, so I always tell my students here, when I equals 1, you're gonna see the variables y0, y1, y2, and x1. So it always looks like a mountain shape, right? See, it's like a mountain shape. You know, actually the Chinese character for the mountain is this. Does it look like a mountain shape? Okay, so let's simplify it. 4 times 2.5 is 10. 10 minus 1 is 9. Y0 is actually -1. And then minus 8 times 2.5 is 20. So 20y1 plus 4 times 2.5 is 10. 10 plus 1, 11. Y2 equals minus 2.5. So we can move all the constant to the right. So we get minus 20y1 plus 11y2 equals, this is minus 9, move to the right, become plus 9. 9 minus 2.5 is 6.5. So this is the first equation. Second equation, we want to plug in I equals 2. So far, so good. So our mountain looks like this. Okay, but I don't want to draw too many mountains here, then you don't see, it's quite messy. You won't see what I write, right? So for x2 is 3. Minus 1, then here we have y1 minus 8 times 3, y2 plus 4 times 3 plus 1, y3 equals minus x2 is 3. Okay, so what do we get here? 12 minus 1 is 11y1 minus 24y2 plus 12 plus 1, 13 y3 equals minus 3. See, it's already in a good format, so we don't need to change anything. And then I equals 3. Wow, the mountain is right here. So 4 times 3.5 minus 1, y2 minus 8 times 3.5 y3 plus 4 times 3.5 plus 1 y4 equals minus 3.5. But y4 is actually 10. 4 times 3.5, what is that? Okay, 4 times 5 is 20, 4 times 3 is 12. So this is 14, right? So 14 minus 1 is 13, right? So we have 13, y2 minus 8 times 3.5. We can actually think of that. We borrow 2. 2 times 3.5 is 7. And then 7 times 4 is 28. y3 plus 14 plus 1, 15. y4 is 10 equals minus 3.5. Oh, so we can move the constant to the right hand side. So move this constant to the right. We get 13y2 minus 28y3 equals minus 150 minus 3.5 is minus 153.5. So far, so good. So now we get 3 equations. This one, and that one. The first one gives us minus 20y1 plus 11y2 plus 0y3 equals 6.5. Second equation, 11y1 minus 24y2, 13y3 equals minus 3. Last equation, 13y2 minus 28y3 minus 153.5. So the first column corresponds to coefficient of y1, second column corresponds to coefficient of y2, third column corresponds to coefficient of y3, last column is the right hand side. So this matrix, use your graphing calculator to reduce echelon form. Then we can get the identity matrix and the solution for y1, y2, y3. Okay, let's see. So I'm gonna show you in MATLAB or Octave. So we have the matrix B now equals minus 20, 11, 0, 6.5. 11 minus 24, 13 minus 3, 0, 13, negative 28, negative 153.5. Okay, so this is B, and we want to do reduce action form, reduce row action form of it. See? So this is the answer we get, and actually I already print screen here. So we get our y1 is, this is our y1, this is our y2, this is our y3. So far so good, everybody? Yes, so that is our answer. And if we do the finite difference formula, and you can see, so how do we input the P, Q, R? So here, the left hand point is 2, right hand point is 4. We divide it into, so this is like A, this is like B, this is N, and this is P, Q, R. This is YA, this is YB. Okay, what is P in this case? Remember, if you want to see PQR, you have to solve for Y prime prime. Okay, so how do you solve for Y prime prime? Well, XY prime prime equals, oh, sorry, let me use a different color so that you can see what we are doing. So XY prime prime equals minus Y prime minus X, right? So y prime prime, both sides divided by x. So minus 1 over xy prime, and then x over x is 1. So the p is the coefficient of y prime, but you see there's no y there. So q is 0, and then r is negative 1. But think about p, q, r, they are vector functions. Okay, so that's why here when you input your p, if it's 1 over x, you want to have minus 1 dot slash x. That means it's a vector, and each entry is minus 1 over the corresponding entry in the x vector. And q is just zeros, so but we want a vector, a 0 vector, so it's a 0 vector with dimension 1 column and 3 row. And then r is minus 1, but we want it to be a vector, it's a constant vector, minus 1, so we do minus 1 times 1s with the dimension 1, 3. Okay, and then you can see this is finite difference formula, and you can see that our answer match with the results here. So far so good, everybody? Okay, so today we talk about the finite difference method, and we do 2 examples. So we will continue in video part B. See you soon. Bye.